Hello, Chem 30. Welcome to week 5 of our distance learning adventure together. We are officially entering a new unit, guys. Unit B is done on redox chemistry, and we're moving into organic chemistry. This is normally the shortest unit of Chemistry 30. And this is going to be interesting going through it this way. In my opinion, it's usually the easiest one. I'm not sure if it's going to come across as the easiest when we're going through it this way. So one of the things I wanted to do this week, just to give you an opportunity to ask questions in a more formal setting, is we'll do a Zoom meeting. Google Meet meeting on Thursday. And I put this into the weekly email. It's scheduled for Thursday morning at 11 o'clock. I'm going to do my Chem 20s at 10 o'clock. Now, it's completely optional, totally up to you if you want to come. However, it's a good opportunity to bounce some ideas off of each other and to ask some questions, especially considering the new material. Now, in terms of accessing that Google Meet, the information will be posted up on our Google Classroom on Thursday morning. So check it out there if that's something that interests you. Alrighty, so in the meantime, here we go, guys. Now, organic chemistry, in terms of an introduction to it, is going to be our focus this first week. Ultimately, guys, organic chemistry is a pretty big deal. It's a big enough deal that it gets its own separate branch. And from a focus perspective, it's all about carbon, and it's all about how carbon bonds with itself and with other things. And part of the reason why that's such a big deal in human lives is when you look at the Earth and the living things on Earth, massive amount of what makes us is based on carbon. We are carbon-based life forms. You may have heard that before. Now, granted, we're not going to go into the detail that we would if we were in class, but we'll still give you enough of an outline of an introduction that you should be able to confidently understand the tip of the iceberg of organic chemistry, if you will. Now, first of all, when we think about the molecules that you encounter on a daily basis, like I said, so many of them are organic. It's not enough to just have carbon to make you an organic compound. But I would say some of the huge ones, if you guys have taken Biology 20, that come to mind are your carbohydrates and your lipids, your fats, and here's the ringer of them all, your proteins, right? All of these are organic compounds. And these are the building blocks of life on Earth, right? And your proteins in particular end up making up all the enzymes, all the different hormones. So ultimately, you would not exist if we didn't have organic chemistry. So understanding this as a branch of science is a pretty big deal in terms of knowing how life exists, how life works, and how we proceed from here. If organic is carbon-based, there is one group of carbon-based molecules that are still considered inorganic. And these are the ones where you've got carbon in something like a polyatomic ion, like carbonate, and in cyanide, right? So both of these, carbon is acting from an ionic perspective. So that's a little bit different. Same thing with a carbide. Again, carbon is acting in a way where it is forming ionic compounds. One other exception is oxides of carbon. So for example, carbon dioxide, carbon monoxide, both of these are not in the branch of organic chemistry and the actual study of organic chemistry. We are focused with organic chemistry on molecular compounds. This is key, right? Where you're dealing with that full sharing of electrons and of carbon attached to carbon and attached to hydrogen, for example. Within the context of the notes this week, there's a number of videos, especially at the introduction, that it's worth watching. They're not essential videos, but I think they're quite short and they're just well put together. And they give you a good, especially considering this is an introduction to something new, a good broad outline of what we're doing. So when you're looking at the notes, you'll see those words that are in blue and underlined. If you click on those and hover with those, that's where you'll link to it. Now, the videos I'm attaching you to, you don't have access to yet. You're going to have to use my username and password to get into them. If any of you are having issues doing that, let me know, speak out, and we'll figure out how to get you on there. It's a free resource right now. Usually it's not, but with all of the COVID-19 shenanigans that are going on, hey, a lot of things are now free from a home perspective that weren't before. Okay, so moving on to diversity of our organic compounds. One of the reasons why, and diversity, by the way, means that we've got many different things, so many possible combinations. Part of the reasons for this is incredibly high bonding capability. When you think about carbon, it has the ability to bond 4 times, which is a significant thing. Now, it could be bonded to other carbons, or it could be bonded, in the case where we start, to a lot of hydrogens. Eventually, in Chem 30, we'll talk about it bonding to oxygen as well, and to some of our halogens, chlorine, fluorine, iodine, etc. Don't get me wrong, nitrogen has a big part in this too, but for this unit of Chem 30, we're not going to look too much at the nitrogen bonding. If you decide that you're taking organic chemistry in university, it's an incredibly interesting course, and it's an incredibly knowledge-heavy course. The word is erudite. The knowledge is insane. So just be aware, if you like this organic chemistry stuff, this seriously is the tip of an iceberg, guys. What you will encounter from a university perspective when it comes to organic chemistry is awesome, interesting, and seriously intense. Okay? Now, another thing with the diversity of organic compounds is they can form some lovely, not just single bonds, but double and triple bonds. Our focus this first week is going to be on the single bonds formed. We'll get into the double and triple next week. And the other cool thing is long chains, which means we end up with something called polymers, and that'll come up a little bit more later, and also rings. We'll barely touch on rings this week. These are called cycloalkanes this week, so cyclo meaning cyclical, but I mean, there's some very cool ways that carbon can form different types of structures. So if you're curious about it, definitely do some research on your own, check it out. Alrighty. Let's move on to another keyword. Again, I recommend that you check out the video on isomers that I've posted with the notes. Isomers and organic compounds are a big deal. Essentially, they have the exact same molecular formula. So in other words, we're dealing with really simple hydrocarbons this week, combinations of hydrogen and carbon. And we could look at 2 different molecules with the exact same number of carbons and the exact same number of hydrogens. And yet, they can form quite a different structural formula. And if the structure is different, that means that the way that they interact with other molecules is different. So it changes their properties a lot. We're not going to go into too much detail on this, but I thought I'd just mention it. I talk a lot more about it in class. Thalidomide is a type of molecular compound where 2 different isomers are a really big deal. So if you look on the left versus on the right here, these 2 are essentially mirror images of each other. And they're 2 different isomers. We end up with a situation where one of them caused severe deformities in unborn children. That's what I'm showing you up here in this picture, and here in this man who has no arms. They're called thalidomide babies. And ultimately, having one isomer versus the other made something very, very potentially impactful in a negative way, whereas the other isomer would have no impact on an unborn child. So isomers, like I said, it's called stereoscopy. It's how some molecule sits in space. And an isomer from one type of a hydrocarbon to an isomer of another one totally interacts in its space differently. Okay, let's check it out with a more simplistic example. 2 isomers of this entity, C4H10. We'll talk more about the naming of this later, but just so you know, this is butane. You could have found it in your formula sheet if you wanted to. And butane with these 4 carbons and its 10 hydrogens looks like this. So I want you to draw it out in your notes. The 4 carbons are all single bond joined, okay? And we're going to write this out in a great big structural diagram. And each of these carbons has to bond 4 times. So this carbon, for example, is bonded to one other carbon and 3 hydrogens. And this second carbon has 2 hydrogens, but also 2 carbons. That's 4 total. We've got hydrogen here, and then we've got 3 coming off of this end one. Again, this structure is dictated by the knowledge that carbon has to bond 4 times. And if you count everything out, indeed, we've got our 4 carbons and our 10 hydrogens. Now, I want to be clear, and this is going to start to come up more and more as this week continues. Simply putting a bend in the carbons, for example, something like this, doesn't change the structure, right? This is still the same. And the way that you can tell that is by looking at the actual straight line of carbons. I'll highlight it here to show you what I mean. I can still draw a nice straight line of those 4 carbons, and even though this is bending around, I can still bend, or I can still have this full continuous line. I don't have to lift my pen to make that line, if you will. Okay? So there's one of our isomers. Now, ultimately, we absolutely have, and again, both of these are the same, guys, same. This is not 2 different ones, those are identical. We have 4 carbons and we've got 10 hydrogens. But what if we change things up a little bit and check out this one? We'll talk more about how these are named, like I said, later, but this one's methyl propane. We have prop here, something different. But watch what happens still. If we take this, and what if we put 3 of our carbons in a row, and then instead of putting a carbon on either end, we put another carbon right in the middle. Oh, so still 4 carbons. In other words, our C4 has completely held true. Now, let's put the hydrogens on. Remember, every carbon must bond 3 times. So this first carbon needs an extra 3 hydrogens on it to get it to 4. This top carbon needs an extra 3 hydrogens to get it to bond 4 times. This side carbon to the right needs 3 more hydrogens. And now this middle one down here, I just need a singular hydrogen. Every carbon is bonded 4 times. Let's count out these hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, check that out. We still have 4 carbons and 10 hydrogens. Structure-wise, though, this is quite different. So look, here's methylpropane, C4H10. Here's butane, C4H10. Identical molecular formula, quite different structure. This one's in a nice row. This one, not so much. I cannot draw one straight line of carbons. I end up instead with a situation like this. So definitely different. Now, in terms of what's the big deal here? Well, actually a pretty big deal. It changes the boiling points and like melting points. It changes essentially how attracted these molecules are to each other. So for example, butane, going back to this one, will boil at negative 0.5 degrees Celsius. Sorry, the pen's not writing there, okay? Whereas if we go to our methylpropane, it's going to boil at minus 12 degrees Celsius. That's a significant difference. One is just below 0 and one is quite a bit lower. So in terms of when they turn into a gas, it's quite varied. In other words, if my methylpropane has a lower boiling point, that means that the London dispersion forces, pulling back some Chem 20 stuff, the London dispersion forces between these methylpropane molecules are just not as strong. Why aren't they as strong? Look at the shape. These molecules can't get quite as close to each other. They can't get quite as close, then they're not able to induce the same dipoles as a nice, more spherical shape of butane can. Therefore, butane has a higher boiling point. Higher London dispersion forces, harder to boil. Lower London dispersion forces, a little easier to boil. Okay, let's keep going here, guys, and talk a little bit more about how we actually communicate drawing these guys. So check it out that when we model these, lots of different ways to do it, but we're going to focus on 3 different ones. The first is the same that I just showed you for butane and methylpropane, the complete structural diagram. Pay attention, please, in questions to what you're being asked to do. If you draw the wrong type of diagram than what is being asked for, then you are not answering the question, and I will take off marks. You got to answer what is asked of you. Okay, the one we're going to focus on first here is pentane, and I will tell you that pentane is C5 and H12. Now, we'll talk more about how I know that in a moment, but ultimately with a complete structural diagram, every single atom is shown, no exception, and every single bond is shown. If you're asked to draw these, the reaction is kind of like, oh, because they're kind of annoying. You have to draw every little thing, and it gets frustrating. So pentane, we're just in one straight line, 1, 2, 3, 4, 5, 6 of them. Right? Oh, sorry. Pentane. How about 5? There we go. Okay. Okay. So our 5 carbons are there. Now you have to draw every single atom, so we have to put our hydrogens on. Remember the key word, carbon bonds 4 times. This has to be your focal point of all of organic chemistry. This first carbon is bonded once, so I need to add another 2, 3, 4 bonds. On each of those bonds is going to be a hydrogen. That's how these hydrocarbons work. There is an endless number of hydrogens we can put on to get our carbons bonded 4 times. Moving on to the second carbon. It's already bonded twice, so I need 1, 2, 3, 4 bonds total. Again, we put hydrogens on those bonds. Moving on to the third. Has to bond 4 times, put hydrogens above and below. The fourth carbon, same thing, hydrogens above and below. And our last carbon is going to need 3 hydrogens because it's on the end. There is our pentane. Again, this is a complete structural diagram. Kind of a pain to draw, not going to lie. Let's go into something that's a little bit easier. These are your condensed structural diagrams. You'll be doing a lot of these. Now, with a condensed structural diagram, you don't actually show the individual carbon-hydrogen bonds. You still have to make note that the hydrogen is there, but you don't have to show every individual bond. I'll show you what I mean. We're still going to focus completely on pentane for each of these so that you can see the difference between the different types of ways to draw these organic molecules. So when I draw these, what I always do is I draw my carbon and then I leave a little space for where the hydrogens are going to go. And then I draw my line for my bond. So moving on to this one then, beside that bond, I'm going to draw the carbon right away, then leave a little space. And then I'm going to draw the carbon, leave a little space, carbon, leave a little, sorry, my dog's barking. Leave a little space, count them, pentane, we need 5. 1, 2, 3, 4, 5. Okay, if those are our 5 carbons, to add on the hydrogens, again, think to yourself, every carbon has to bond 4 times. So this first carbon is bonded once to the carbon beside it. It needs 4 in total. So in other words, we're going to have to add 3 more hydrogens. That's 4 bonds total. The second carbon is already bonded twice. So to get up to 4, we add 2 hydrogens. Third carbon bonded twice on either side. Add 2 hydrogens to get to 4. Fourth carbon, same pattern. Add 2 hydrogens to get to 4. The carbon on the end must bond 3 times. It's only bond once to the left. I need 3 more hydrogens to make that pentane. Notice it is still C5H12. If you count this out, you can see it. I've got 3 plus 2 is 5, 7, 9, 3 more is 12. C5H12 has not changed, but this is a condensed structural diagram. Like I said, you will be expected to draw these quite a bit. We do a lot of them. And the last one, which is a line structural diagram, do a lot of these too. This is one that you should be quite familiar with. We use them a lot. Ultimately, for a line structural diagram, we are entirely focused on lines to represent bonds. These are very, very simplified. Some people really like these because they find them easy to look at. The big thing for this is that there are no hydrogens actually drawn in. They still exist. It's not that they're not there, but you have to recognize how many, and you have to be able to look at that and understand that. And that's where these are sometimes tough for some people. Ultimately, do not lose sight that every single carbon has to have as many hydrogens to make sure it's bonded at least 4 times, okay? Or not at least, has to be 4 times. Let's check out pentane. We start with a single carbon, right? I don't even need to draw a dot or anything, but as I move up, oh, that's the thing with this thing. It doesn't let me draw straight lines very well. I'll do my best, okay? I think if I go faster, it'll help. 1, 2, 3, 4. There we go. Okay, these are supposed to be straight lines. I don't know. I find it hard with my stylus to make that happen. Anyway, I'm going to go with red to show you where or here, highlighter, show you where these are. We have a carbon right on the end. There's the first one. Here's the second carbon, the third, the fourth, and the fifth. Now, for a line structural diagram, you wouldn't draw those little highlights in, right? It would just be the line. But what you have to recognize is that very first carbon is actually CH3, right? It's got 3 hydrogens on it. This second carbon is actually CH2, 2 hydrogens on that carbon. This lower one is actually CH2. This one up here, CH2, and the end one, CH3. We don't write those in though. It literally, for a line structural diagram, is as simple as done, finished, 5 carbons, okay? So like I said, lovely and easy to draw. Some people struggle to interpret it properly. When it comes to, for example, determining molar mass of these guys, if you miss a hydrogen, you just messed up the whole question. So it's really important that you are paying attention to the details, which in the world of chemistry, that's always the name of the game. Okay, let's look at a couple questions related to these. This is right from your notes. We're going to focus on isomers again. There are 2 other isomers of C5H12. If you think back originally, in terms of these questions, we were just talking about C5H12 in terms of drawing these organic molecules, right? So if we consider that we've got some other isomers of these, we're going to write a condensed structural diagram and then a line structural diagram for each of these. Now, that's where I'm saying pay attention to the language. Condensed, you have to know what those mean, versus line structural diagram, again, you need to know what those mean. Okay, let's begin. The original starting point for you to do these, I think easiest, is draw out C5H12 at its most simplest. In other words, let's draw it with our 5 carbons in a straight line. Now remember what I said, with condensed, start with a C, leave a little space for the H's, draw your line. Then a C right beside, little space. C right beside, little space. C right beside, we're at 4 and 5. There's our 5 carbons in a row. For condensed, you now need to put in your hydrogens. Any of the ones on ends are going to have 3 to make them bonded 4 times. If they're in the middle here, 2 hydrogens. Now that carbon has 1, 2, 3, 4 atoms bonded to it. And H2, H2 for these middle ones. Back to the end, CH3. Okay, here's our starting point to get that first isomer. So here's one, right? There's an initial one. Now, what we're going to do is move things around, play around with it. Now, just bending it isn't enough. You have to actually make a new structure. So if I take this carbon and say move it onto here, let's see what we end up with. And isomer number 1. I now have 4 carbons in a row, right? So I'm going to go 1, leave a little space, another carbon, leave a little space, another carbon, leave a little space. There's those 4 carbons. Remember, I moved that first one onto here. So I still have 5 carbons, but this is distinctly different. At the beginning, it's one lovely straight line. Down here, I can't make a straight line between those 5 carbons anymore. There's a bend in there that can't be straightened out. It's not like a string that I've squished all up, and when I straighten it again, it's perfectly straight again. I can't with this. Okay, start putting your hydrogens in. Anything on the end is going to have 3 because it has to bond 4 times. So this is a CH3, but the one hanging out down here is now a CH3. Otherwise, that carbon won't have bonded 4 times. Now pay attention to this carbon here. This one's already been bonded 3 times. So I have to put a single carbon on there. It's the first time we've had that happen. Moving on beside, it's bonded twice, so I put 2 more, and the one on the end back to CH3. We still have our C5H12. Count. 3 plus 3 is 6, 7, 8, 9, 10, 11, 12. C5H12 hasn't changed. And that's key, guys. If you somehow miss a hydrogen, you are creating chemistry. You can't do that. You can't just make things up here. It has to match. Okay, that's your condensed structural diagram. Let's do the line diagram. Focus always on the longest chain, which in this case now is 4. So we'll draw our line for 4, which goes like so. 1, 2, 3, 4. I know that seems weird because I drew 3 slats, but let me go back to the highlighters again to show you what I mean. Here's the first carbon, 1. Here's the second carbon, 2. Third carbon, and 4. See, so it is a chain of 4. Now we have to put that one extra one that's hanging down below, this one right here. So to add that in, you simply take a line and extend it down. Done and done. And that is our 5th carbon. There's your line structural diagram for that isomer. Okay, let's go to the second isomer of this guy. Second one. Now, same thing. Think about that starting point where you've got the 5 carbons all in a row, right? This guy. But instead of us moving that first carbon where we did, now I'm going to move it into the middle. And, whoops. And then I'm also going to, I shouldn't change to those, already in the middle, but I'm also going to do something funny and move this one over. Ooh, that changes things a little bit. Hey, another isomer. Think about how this thing goes. Now we're going to have a carbon in the middle, and we're going to have a carbon off to the side. Make sure you leave room for the hydrogens, carbon here. Then we've got one coming out the top, one coming out the bottom. This is still C5, so we're good. Make sure every carbon is bonded through 4 times. CH3, 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 and CH3 to all of these end ones. Check out the middle. I'm not going to add any hydrogens there. It's already full. It's been bonded 4 times. Count those hydrogens, 3, 6, 9, 12. Oh yeah, this is C5H12 without a doubt. In terms of the line structural diagram for this one, loop, loop, done. Okay? Think about where your carbons are. 1, 2, 3, 4, and 5. It's all listed there. Okay. Key thing. Every carbon must be bonded 4 times, no exception. There's one more question on here, guys. This is talking about, again, isomers, but this time it's of isomers of C6H14. Notice the question is identical. Write out the condensed structural diagram. Then write out the line. Oops, I see I missed a letter there. Line structural diagram for at least 3 of the isomers. This is similar to a question you're going to have to do in your assignment this week. Now, ultimately, I'm not going to go through this whole question on here, but follow the same process, guys. Your step 1 is write it out as your 6 carbons all the way across. 1, 2, 3, 4, 5, and 6. For the condensed structural diagram, put in the hydrogens where they're required, double check, make sure you've got 14, and now start to play with this. It's little puzzles. Start to build it into different isomers, okay? Now, one of these isomers, for example, that you would end up getting, I'll show you this one, you would get CH3 attached to a carbon here with another CH3 on top, another CH3 on the bottom, attached to a CH2, and a CH3. Look at that, 6 carbons. Let's talk about how you would do this with a line structural diagram, just to clarify. Look for your longest chain of carbons, okay? For example, if you go like here to here, that's a chain of 3, and that's fine, but that's not the longest we can do. Let's see if we go like this. Oh, there's a chain of 4. Lovely. There's other chains of 4 you could do. this will actually give you the exact same answer. What if I make my chain like this with the blue? If you consider the shape of that and where things are coming off of, either way, you still have 2 carbons coming off of this one, no matter which way you go about it. So just be aware, whether you do the green or kind of the turquoise, the line structural diagram doesn't change. Okay, so we've got 4 is my longest length. 1, 2, 3, 4. Now off of this second one here is where there needs to be 2 carbons coming off of it. Okay, how do you do that? Well, there's a variety of ways that people draw it. I like to draw them both coming off of the top one, or if it had been flipped off the bottom. So we go 1 coming here, 2 there. There it is. Count them out. 1, 2, 3, 4, 5, 6 carbons. And both of those carbons are coming off of that second one going across. All right, guys, you should please try out the first question in the assignment, number 1 in weekly assignment 5. Helps you to get a feel for isomers, getting used to drawing these condensed structural diagrams, the line structural diagrams. Next podcast, we're moving on to alkanes.